Lesson 5, Symmetry and Polynomial Functions. And this is the last lesson of the first unit of the Advanced Functions course. In this lesson, we're going to look at special types of polynomial functions called even and odd polynomial functions. So before we do this lesson, you have to remember what I taught you earlier about line symmetry and point symmetry. So there's the definitions for you again, just so you can read them quickly. Line symmetry is if there's a vertical line over which the polynomial remains unchanged when reflected. And point symmetry is when there is a point about which the polynomial remains unchanged if you rotate it 180 degrees about that point. Now let's move on to section 1, where we learn about two specific types of polynomial functions, even polynomial functions and odd polynomial functions. Now the first thing we have to establish is that a polynomial function of even or odd degree is not necessarily an even or an odd function. Now it's one of those things where all even functions are even degree, but not all even degree functions are considered even functions. And same thing with odd. All odd functions are odd degree, but not all odd degree functions are considered odd functions. So how do we establish if something is an even or an odd function? I have this table here that I'll walk you through that it establishes that for you. So an even degree polynomial function is an even function if it meets the following criteria. It has line symmetry, and that line symmetry has to be at the y-axis. And that happens if in the equation of the polynomial function, the exponent on every single term is even. If you have any terms that are odd degree, then the function is not an even function and it wouldn't have line symmetry at the y-axis. And even functions are allowed to have a constant term. Because constant terms, you could think of a constant term like, let's say 5, you could think of that as having an x to the 0, and for all purposes for this, we could consider 0 as even. Before I talk to you about this algebraic rule that we have for all even functions, let me just show you one in Desmos. So let's make up an even function. For it to be an even function, all the terms have to be even degree. So let's say 3x to the 4 plus 2x squared, and it can have a constant term, so let's say minus 2. There's an even function. Notice it has line symmetry about the y-axis. If I drew a vertical line through an x value of 0, notice the function, if reflected across that line, would remain unchanged. Now let's look at the algebraic properties of this. So I'm going to plot a point on this graph. And notice, if I were to evaluate the function, let's say, okay, I have it at an x value of 1 right now, and let me get that to label it. At an x value of 1, watch what happens if I move that point to an x value of negative 1. Notice that it's at the exact same y value. And actually, let me get Desmos to show us the y value. There. So when x was 1, the y value is 3. When x was negative 1, the y value is 3. How about, let's say, if x was 0.5? The y value is that negative 1.3 approximate value. How if I make it negative 0.5? Same thing. The y value remains unchanged. So that's where this property comes from. If it's an even function, f at negative x equals f at x. And here's an example of that for you with this function. This function is 2x to the 4 plus 3x squared minus 2. That's pretty similar to the one I showed you in Desmos. And it's just showing you that f at 1 and f at negative 1 are equal to each other. And that's true for any value of x if we have an even function. Now let's talk about odd functions. An odd degree polynomial function is an odd function if the following conditions are met. It has point symmetry at the origin, so it has to have point symmetry, and that point symmetry has to be at the origin for an odd degree polynomial function to be considered an odd function. And that happens if the equation of the function, every single term, is odd degree. That means it can't have a constant term, because we consider constant terms to be even degree. Now, before I talk to you about this rule, let's go back into Desmos and let's make up an odd degree function. Like, let's make these all odd degree terms. So I can make that 5 and 3 and put an x to the 1 on that. Let me zoom in a bit here. Okay, so at an x value of 0.5, the y value is that negative 0.656 approximate value. What's the y value if I make x negative 0.5? Notice it has the same absolute value, but the sign is different. It's now positive 0.65625. Let's try another x value. How about an x value of 1? The y value is 3. So what's the y value going to be at an x value of negative 1? It's not going to be 3. It's going to be the opposite sign. It's going to be down here at negative 3. So the rule we have here, f at negative x isn't the same as f at x. It's the same as negative f at x. So they're the same, but they have the opposite sign. That's what this rule is telling you. And then there's an example below that shows you for this function here, which is an odd function because both terms are odd degree. It shows you that f at 1 and f at negative 1 have the same absolute value answer, but opposite signs. So f at negative 1, this number, is equal to this number multiplied by negative 1. So f at negative 1 equals negative f at 1, and that's what the rule tells you here. For this example, it asks you to write down if the function is even or odd and how you know. So I've given you an excess of information here. I've given you the equation and the graph. We should be able to tell from either or whether it's an even function, an odd function, or neither. So this one, I can tell this is an odd function, and let me explain to you why. So first thing I'm going to write, it is an odd function. And I know that for two reasons. From the equation, I can tell it's an odd function, because in the equation, both of the exponents, remember this one has a 1 on it, both of those exponents are odd. So both terms are odd degree, meaning that it is an odd function. From the graph, I can tell this is an odd function because it has point symmetry at the origin. If I were to rotate this function 180 degrees around that point, it would look unchanged. Part B. This one, I can tell from both the equation and the graph that this is neither even or odd function. Yes, it's an odd degree function, but it is not an odd function. How do I know that? So I'm going to write neither. How do I know that? Well, from the equation, I can tell it's not an odd function because it has a mix of even and odd degree terms. We have odd degree term, and this one, remember, has an x to the 0, which we consider an even degree term. Odd functions cannot have constants, and this one does. So this one is neither even or odd function. And from the graph, I can tell it's neither, because although it does have point symmetry, that point symmetry is about this point right here, the point 0, 2, which is not at the origin. So that means neither even or odd. Part C. So part C, I can tell this is an even degree function, but is this even degree function also an even function? Yes, it is. I can tell that from both the equation and the graph. I can tell from the equation because if we look at all the terms are even degree. Degree 4, degree 2, and degree 0. Those are all even. And from the graph, I can tell that this is an even function because it has line symmetry, and that line symmetry is right down here, right down the y-axis. Part D. This is an even degree polynomial function, but is this even degree polynomial function also considered an even function? No, it's not. So we'd write neither. So neither even or odd. And how do I know that? From the equation I can tell because there's a mix of even and odd degree terms. Even degree, odd degree, even degree, even degree. So there's a mix of even and odd, therefore it's neither. And from the graph I can tell it's not even or odd because it doesn't have line symmetry at the y-axis and it doesn't have point symmetry at the origin, so it's neither. In fact, this graph has no symmetry. Part E, our last one. So this one, I can tell from the equation and the graph that once again this even degree function is not an even function. It's neither an even or odd function. I can tell from the equation because there's an even degree term and an odd degree term. So once again, a mix of even and odd degree terms means it is not considered an even function or an odd function. And from the graph, although this function does have line symmetry, that line symmetry is not at the y-axis. It's at the line x equals -1. So since the line symmetry is not at the y-axis, we can't consider this an even function. Let's move on to example 2. I just give you either the graph or the equation this time, and we circle all that apply. So for part A, if we look at the graph of the function, I can see that there is point symmetry, and that point symmetry is right there at the origin. So because it has point symmetry at the origin, I can circle point symmetry, and because it's at the origin, I know that means that this is in fact an odd function. Part B, this is a weird looking function, has no symmetry at all. We can just circle no symmetry, and if it has no symmetry, then it's not an even or an odd function. Part C, I have a special little note here. There's a mix of even and odd degree terms, right? Odd degree, even degree, and the constant we consider even degree. So mix of even and odd degree terms. So it can't be considered an odd function or an even function, but that doesn't necessarily mean it has no symmetry. It could have symmetry, just not at the same place that would make it an odd or an even function. And in fact, all degree 3 functions have point symmetry. So this function for sure has point symmetry. That point symmetry would just not be at the origin. So we'll make a note. All degree 3 polynomial functions have point symmetry. Part D, we just have the equation, we don't have the graph. So in the equation, I see 3 terms, and all 3 terms are even degree. Degree 6, degree 2, and degree 0. All of those are even degree. That makes this an even function, and all even functions have line symmetry at the y-axis. We can circle line symmetry. Part E, we just have the graph, and I can tell from this graph this function has line symmetry right here at the y-axis. That makes it an even function. So I can circle line symmetry and even function. Part F, this function does have line symmetry right here about the line x equals 2, so I can circle line symmetry, but I could not circle even function because that line symmetry is not at the y-axis. And part G, all 3 terms are odd degree. Degree 5, degree 3, and degree 1. Since they're all odd degree terms, that makes this an odd function, which means it has point symmetry at the origin. Example 3 says, without graphing, determine if each polynomial function has line symmetry about the y-axis, point symmetry about the origin, or neither. And it says verify your response algebraically. That's going to be the new part of this question. Like, I can tell from this equation that this is an even function because all 3 terms are even degree. So it is an even function. And do you remember the algebraic property for even functions? The algebraic property tells us that if it's an even function, f at x would be equal to f at negative x. And let me just remind you of that in Desmos. Let me put up this equation. Okay, here's that function. Notice if it's an even function, if I were to evaluate, let's say, f at 1, I get 1. If I evaluate f at negative 1, let's move the point to an x value of negative 1, it has the same y value. Y value is still 1. And that should be true for any x value we choose. If we do f at 4 or f at negative 4, same y value. F at 0.5, oh, and there's the point. It would have the same y value as f at negative 0.5 because it's symmetrical about the y-axis. So all we have to do is algebraically prove that f at negative x is equal to this. So let's do that. Let's get an expression for f at negative x and show that it's the same as f at x. So f at negative x would be equal to, well, all I have to do if I want an expression for f at negative x is replace all the x's in this equation with negative x, and then simplify. So I would have 2 negative x to the 4 minus 5 negative x squared plus 4. And we can think of this negative x, that's the base of the power, think of it as a negative 1 times an x. And if you know your exponent rules, the exponent goes on both the factors of the base. So I would have to put the exponent of 4 on the factor of negative 1 and on the x. And same with this power over here. I would have to put the squared on the factor of negative 1 and the x. And then if we simplify this, negative 1 to the 4 is 1, and negative 1 squared is 1. And anytime we have a negative base with an even exponent, it becomes positive. And that's the foundation of why If we have an even function where all the terms are even degree, meaning they all have even exponents, we're going to get f at x equal to f at negative x. So if I simplify this, I would have 2 times 1 times x to the 4 minus 5 times 1 times x squared plus 4. Notice my expression for f at negative x is exactly the same as my expression for f at x. So in my conclusion, I can say f at x equals f at negative x. And what does that tell me? Therefore, an even function that has line symmetry at the y-axis. Part B, I can tell from the equation this is an odd function. All terms are odd degree. But let's prove that algebraically. What's the property for odd functions again? F at negative x equals negative f at x. And let me remind you of that in Desmos with this function. Okay, there's the function. You can see that it has point symmetry at the origin. And let me prove the algebraic rule to you. So right now I have f at 0.5, and we see the y value is 2.031. If I do f at negative 0.5, it should have the same absolute value, but it should be negative. So it should be negative 2.031 as the y value. Let's check. And there it is. And that should be the same for any x value. So let's say x at 1, I get a y value of 8. X at negative 1, I should get a y value of negative 8. And there it is. So that just proves the relationship. F at negative x is not equal to f at x. I would have to multiply the f at x value by negative 1 to make it equivalent, because it has the opposite sign y value. So f at negative x equals negative f at x. So if we want to prove this algebraic, I'm going to have to get an expression for negative f at x and f at negative x to show they're equivalent. I think the easier one to do would be negative f at x. If I want negative f at x, I just have to multiply this whole expression by negative 1. So it would be equal to the negative of this function. And if I simplify this, just distribute the negative to all 3 terms. That just changes the sign of all of them. So it becomes positive 3x to the 5 minus 9x cubed minus 2x. So this is an expression for negative f at x. Now let's get an expression for f at negative x and show that it's equivalent to what we just found here. So if I want f at negative x, I have to switch all of the x's to a negative x. So negative 3 times negative x to the 5 plus 9 times negative x cubed plus 2 times negative x. And remember, an exponent goes on both factors of the base. So that exponent of 5 would go on the factor of negative 1 and on the factor of x. Same with this term. The exponent of 3 goes on the negative 1 and the x. And this term, 2 times negative x, is just negative 2x. I can simplify that now. When I do a negative base to an odd exponent, the result's going to be negative. So negative 1 to the 5 is actually negative 1. And negative 1 times negative 3 is 3. So the first term is 3x to the 5. And then 9 times negative 1 cubed is negative 9. So negative 9x minus 2x. Notice this expression equivalent to this expression. So we just showed that negative f at x is equal to f at negative x. Therefore, this is an odd function, which means it has point symmetry at the origin. I put a part C in here. I don't think we're going to bother proving algebraically that this is neither. We can tell from the equation, since there's a mix of even and odd degree terms, we know this is neither an even or an odd function. If we wanted to, we could come up with an expression for f at negative x and negative f at x and show that the requirements for it to be an even or an odd function are not met. But let's not bother doing that. We can tell from the equation this is neither. Okay, last example of the unit. Let's just try and connect everything we've done so far. So given this graph, we're going to answer a bunch of questions. Part A says, what are the x-intercepts? So it touches the x-axis here, here, and here. So the x-intercepts are at negative 2, 0, 0, 0, and 2, 0. Now it doesn't ask for what order the x-intercepts are, but let's write them anyway. I know that at negative 2, the x-intercept is order 2, and I can tell that because of the shape it makes. It looks like a degree 2 power function there. It looks like a parabola, so I know that x-intercept is order 2. Same with this one, order 2. But at the x-intercept of 0, it's order 1 because it goes straight through that x-intercept. How many turning points does this function have? So I count 1, 2, 3, 4 turning points. 4 places where the function switches from increasing to decreasing or vice versa. So least possible degree. So when we're finding least possible degree, we have to check 2 things, remember. The least possible degree, well, a function is at least the sum of the orders of the x-intercepts. So based on that, it's at least degree 5. And it's also at least 1 more than number of turning points. So based on that, it also has to be at least degree 5. So our least possible degree, 5. Any symmetry present? If we look back at the graph, yeah, it looks like there is point symmetry about this point right here. If I were to rotate the function 180 degrees around that point, it would look the same. And let me just do that rotation so you can see that. Notice it looks exactly the same that way or that way. So we could say, yes, point symmetry at the origin. And that actually tells us that this odd degree function we have is considered an odd function. Part E says the intervals where the function f of x is less than 0. So when is the function below the x-axis? Let's look. When is this function below the x-axis? It's below the x-axis right here in that interval between 0 and 2, and then also after 2. So in that whole section of the graph, the function is below the x-axis. Now at 2, the function is 0, which is not negative. It's not less than 0 at 2. So when I describe the interval, make sure I only say from 0 to 2, or from 2 to infinity. Interval where f of x is less than 0, I can say x is an element of numbers within the following intervals, from 0 to 2, or from 2 to infinity. And notice round brackets when I'm using that bracket notation to indicate that the end values are not included in the interval. And this u means the union of the 2 sets, or as we read it, we think or. So the function is less than 0 if we have an x value that's either between 0 and 2 or 2 and infinity. Part F says find the equation in factored form. Well, to get the factors, I would have to figure out what factors would give me these x-intercepts of negative 2, 0, and 2. And those factors would be x plus 2, x, and x minus 2. The factor of x plus 2 gives me an x-intercept of negative 2. The factor of x gives me the x-intercept of 0. And the factor of x minus 2 gives me the x-intercept of 2. Now I have to make sure I put the right exponent on each of those factors by checking the orders. So the x plus 2 factor and the x minus 2 factor will be order 2, and the x factor will be order 1. So I have to put a squared on both of those. Now there's an infinite number of functions that have those x-intercepts of those orders. I need the very specific version of this function that goes through this xy point right here, point negative 1, 3. So what I have to do is I have to figure out what stretch factor do I have to put in there to make sure it goes through that point negative 1, 3. So I put the unknown parameter k, and I sub in my x and y from the point that I know it goes through, the point negative 1, 3, and solve for k. So 3 equals k, negative 1 plus 2 squared, times negative 1, times negative 1 minus 2 squared. Now I just solved this equation for k. There's only one unknown here. 1 squared is 1, times negative 1, and negative 3 squared is 9. So I have 3 equals, those 3 factors equal negative 9, so negative 9k, and therefore k equals negative a third. So my final equation for this function, this polynomial function, which I'll call p at x, equals negative a third times those 3 factors, x plus 2 squared, x, and x minus 2 squared. Now you'd actually probably see this factor of x here beside the negative a third, but it doesn't matter the order of those factors. And let's just verify in Desmos that we have the correct version of this formula that matches this graph. Okay, so the question told us we want the graph and we want it to go through this point right here, negative 1, 3, and we figured out that the k value should be negative a third. So let me move this k value to negative a third and make sure it makes it go through that point. And I'll actually have to write the fraction here so I can get the exact value. And yes, it goes through that point right there. Perfect, we have the right graph. Okay, that's it for the first unit. Make sure you try all these practice questions, and make sure you try out the review practice questions, and you'll be ready for the evaluation on this unit.